on a disk floating through space with a tiny sun.
Hey, I'm FTFE and welcome back to the channel that ties stupidity up in a bag and chucks it in a river. Tonight we have another conversation with a concave earther. The past few conversations I've had have been with concave earthers, and they've actually been a lot more constructive and enjoyable than normal conversations with shouty, angry, annoying flat earthers. This is the first time I have had a female opponent. Nothing particularly special about that, but it's nice to have a lady on the show so that we can have a conversation with someone that thinks that has their own views about the world and isn't going to shout and scream at me like a moron. So let's introduce her. The guest today is Ella Fakey. So if you would just like to introduce yourself to the people, tell them where they can find you, and tell them what your position on the shape of the world is.
Hi everybody, so I am Ella Fakey, and I come from Italy, and I came across concave Earth from a university professor in Italy. He was a mathematician, and he wrote 2 books on concave Earth. So my approach on concave Earth is a little bit different because I do not follow Stephen Christ as the other concavers. But I do really find fascinating the concave Earth world, and so I will try to share with you my thoughts on that tonight.
Excellent. So, are you completely convinced that the Earth is concave?
Well, I am, even though, as I will tell you today, there is actually no evidence, because the convex Earth and the concave Earth, as taught by Paolo Emilio Amicoroxas, which is this mathematician professor, is actually a mirror. Like, it's the same thing. And no matter what, we will never be able to tell the difference. And that is because concave Earth uses non-Euclidean geometry. So even if we measure, like with the Tamarack mines, I don't know if you heard about that experiment that they, yes, and with this view, it's actually the same thing, because if we think about a non-Euclidean geometry, and we will think about the Poincare disk. I don't know if you know what the Poincare disk looks like, the non-Euclidean geometry, and yeah, probably you might. Yes. Okay. Good. And so the farther we go up, the more the space is. How do you say? It gets bigger. So because of that, we will never be able to tell the difference, and it will give us the same results either if it's concave or convex. Because one world uses Euclidean geometry and the other uses non-Euclidean geometry. So both have the same result. I don't know if that makes any sense. I'm usually used to saying this stuff in Italian, so excuse me if...
well, you are already more eloquent than the majority of guests that I've had on the show, so you're doing absolutely fine. Thank you. See, I would have to disagree that you get the same results with a convex and a concave Earth, because one of them requires having a smaller local sun. Obviously, the concave Earth would need a smaller local sun, whereas the convex Earth, the normal heliocentric model, has a sun that is far away and a lot bigger with parallel sun rays. So I kind of think that... Yeah, sorry, Karen.
Well, actually, the distances stay the same, and that's because of this particular geometry, which is not like a straight ruler like we're using today, but again, like I said, the more we go towards the middle of the world, which would be the nucleus of Earth, the more the space gets stretched. So it's a deformation of space, and changing the space from Euclidean to non-Euclidean, we can still have the same exact distances. So nothing actually changes. And that's all of this. I will comment on this video, and I will post the book. One of the books of this university professor was translated in English. So maybe you guys will find it very interesting, because he has all the formulas, which are actually very simple inversions. So with these formulas,
yeah, if you can give me the links to those, I will definitely put them in the description.
yes.
Now, you're saying that within the non-Euclidean geometry shows that the measurements are the same, but obviously the convex Earth heliocentric model has a sun at 93 million miles away. That's not going to be the same for concave, is it?
Yes, it is. That's what I'm trying to say, that it's actually the space gets deformed. It's not like like general relativity has a deformation of space due to mass, and this has a deformation of space due to the center of a sphere. So if you start reading about non-Euclidean geometry, you will find that you can have enough.
So what you're saying is that the space towards the center of the celestial sphere, or how you guys describe it, is more compressed, so the distance is seen further.
Yes, that's you could actually say it like that. It's not actually compressed. It's like it's just a deformation of space, and non-Euclidean geometry allows that because it's not Euclidean. And what I find very interesting about non-Euclidean geometry is that we see it everywhere. So the main thing about this debate, would be about geometry and not about all the little things, because the little things, as this mathematician says, are actually the same because of the two geometry used.
Okay.
And if we say the Fibonacci spiral and all of the way nature lives, and nature is actually non-Euclidean, and we see an orange, we will find the little seed inside, and actually the little seed has so much more information than the whole orange, because it can give us a whole tree. So it's not about the size, because the size can have much more than we think.
Right. Okay. I mean, I have many issues with that. The main one being, why can't we see the fact that the Earth is concave? Well, first off, do you think it's like a hollow sphere, or is it like a bowl?
Well, because I really like studying magnets and magnetism, I like it to be the way I see it, it's a torus. So I find it to be a sphere. Yes.
Right.
And you brought up a very interesting point, and that's actually the main point, because your model is based on special relativity, which says that light travels in a straight path in a Euclidean space. But when we invert space, then also light as well will travel in a curve. And what's very interesting, when I was reading Paolo Emilio Micorozza's book, I found all the formulas. So I decided to put them on Python with the help of my friend, because I'm not a computer genius. And we got the Fibonacci spiral from the curvature of light. So I find this very, very fascinating, because, we see this as a divine imprint when we see the Fibonacci, the sunflower double spiral. And when I found it on the formula of the curvature of light, I was shocked. And it's not proof, because like I said, there is nothing that can prove which world is correct, because there are exact symmetry, as this professor says. So, but I do find it very fascinating, as I found the Fibonacci spiral, which is the same pattern we also see under a ferrocell. And so the question you asked is like, why can't we see it that it's concave? Because if light curves, and by light curving, you're like, well, why do I not see light curving? Because this transformation, the angles stay the same. So the thing that will give you the position of an object, it's actually the angles at which light comes to your eye. And that's why refraction changes the position of the object. But with this transformation, the angles stay the same. So the observer will never be able to tell the difference what the path actually was, because we only see the angles at which light comes in our eyes. I don't know if I was able to explain myself.
Yeah, okay. I kind of see what you're saying. I think you're getting the way that refraction works a little bit backwards though, because refraction depends on the change in density over a certain amount of space, what's called the lapse rate. So as you're close to water, obviously the coldest densest air is closer to the water, and then as you go up, the air gets less dense. And then say if you have a meter, you can see how much the density changes over that meter, and it gives you the lapse rate. And then using that, you can calculate things like the coefficient of refraction, which can tell you which way light would be bending based on that. And I've done all the calculations, and the calculations work out that the light would be bending down, showing you what's over a curve.
Yes, I was just talking about refraction, not because that's the reason why light curves. I was talking about refraction because it changes the position of the object. Well, this curvature of light does not change the position of the object. It is a transformation, and the professor called it, well, I can't say it in English, but it's a trasformazioni per raggi vettori reciproci. And it's a simple transformation which will keep the angles the same. So the position of objects will not change. So you'd be like, well, why are you saying that special relativity could be wrong and light could actually bend and it would be shaped like a magnetic field? Well, I started studying a lot, and I came out to Dayton Miller, which had an interferometer, like back in the 1925, and he found light speed anisotropy, which was like very, very interesting. And of course, light should not have an anisotropy; it should be constant in all directions. So people will be like, well, he didn't calculate temperature and all of that stuff. He actually replied, he said, I did calculate temperature. So I started researching more, and I found some more experiments that tell us that there actually is a light speed anisotropy. And you can find Roland DeWitt or Cahill, which have done it with coaxial cables as well as optical fiber. So these are very interesting experiments, and of course the math of special relativity works because it's based on data. But the theory is what accompanies the data, but the data is what we get the math from. So the data will always be correct, no matter what, because that's what we get with our instruments. So I just find it very fascinating how light could actually be a field, in the sense that it would actually be a field. So it would take on the shape of a cardioid, which is also a very interesting shape in geometry.
But why would light take the shape of the magnetic field?
Because light is electromagnetism. Because if you see a magnetic field, it curves. You will not see a magnetic field with straight lines.
The thing about light, visible light that we see, is that it doesn't carry a charge. And that would mean it wouldn't be affected by electromagnetism.
Light is electromagnetism.
Yeah, but it has zero charge. Photons carry no charge, so they wouldn't be affected by magnetism in any way, which is kind of my argument against a lot of flat earthers that say, the electromagnetism from the sky is what a fiber optic gyroscope registers, whereas that couldn't be possible because the fact that light doesn't carry a charge means that it wouldn't be affected by other parts of the electromagnetic spectrum.
Absolutely. Light does not get affected by a magnet. And that is obviously right. And I'm not saying that it will get affected. I'm just saying that it's part of the same thing. So basically this theory, or at least the way I approach it, I'm like old school, so I still believe in the ether. So maybe some people would like to call it in other ways nowadays, but I still like to think about it as the ether. So what we see are actually perturbations of the ether. We're not actually seeing anything, and the photon is actually the dielectric acceleration of the field. And actually Steinmetz, Charles Prometheus Steinmetz, described very well the electric field and magnetic field and what electromagnetism is.
Right. So you said the ether there, which I have a large problem with because you also spoke about interferometers, and obviously the most famous interferometer experiment is the Michelson-Morley experiment, which kind of disproved that the ether was a thing.
Well, I'm very glad you brought that up because I actually have printed the whole Michelson and Morley experiment and publishment. I'm definitely like a nerd. I like to read all of the publishments. Okay. And what's the funny part is that they actually never ever got zero fringes. No. What the problem was that the fringes were never correspondent to the position of the sun and the speed of the earth around the sun. So what they did, they were like, okay, this is just an error. So they put it on the side, and then special relativity came out. But when Dayton Miller came out, he was like, well, these errors did not find any logic because they follow a sidereal cycle and not a solar cycle. And the maximum anisotropy was always found still today on the north-south and south-north, how do you say, on north and south, yeah, right when the Milky Way was our azimuth, or I mean zenith, right when the Milky Way passes by. So that happens 2 times a day, every 12 hours. And every 12 hours, that's where we have the maximum anisotropy of light. So Michelson and Morley gave us 1/6 of the fringes that we were expecting if Earth was actually moving around the sun. But it was not none. It was not zero fringes. And the experiments went a lot of people had interferometers. And so it's actually very interesting. Also, another thing that they found out, that the higher they go up, the more anisotropy they would measure. And in the basements, they would only measure like very, very, very little. So that's also very interesting because in my model, it's the celestial sphere ether rotation. I'm actually not an expert in the model, but I am very fascinated by it.
Okay, so the thing about the Michelson-Morley experiment was that they did it at different points in Earth's rotation around the sun. And the reason they did that was because that should have, the 2 different positions, the Earth would have been moving different speeds, and they should have got different fringe results for the 2 times that they did it. But the fringe difference they got was so small that it was basically put down to experimental error, which completely made sense based on the accuracy of what they had. And the fact that when they measured the fringe difference, but when the Earth was in the 2 different positions, and they didn't get a massive difference in the result, showed that either the ether was still, or that the ether didn't exist. And the idea of the ether being still was kind of ridiculous. So the only option they were left with was that the ether didn't exist.
Right. Well, that's because they were assuming that Earth was traveling 30 kilometers per second around the sun. But if Earth is not traveling, then the results should be very much lower than an Earth traveling through the Earth. And what the funny part is that an error should not have a cycle, but we're seeing a sidereal cycle with these interferometer readings. So that's very interesting.
Okay, now I do admit that the Michelson-Morley experiment, the results can be interpreted in different ways, but then obviously special relativity came along and explained the results, because after the Michelson-Morley did their experiment, it wasn't until then that they considered, well, actually, if the Earth was stationary, then the results would also make sense. But then, obviously, Einstein came along with special relativity and explained the results that they got, which matched with what his math said should be the case. But we have other interferometers and things like interferometric fiber optic gyroscopes, which we can use a similar thing based on the speed of light to measure rotation. And if you look at simple interferometric fiber optic gyroscopes, like this one, it shows that as light is traveling through the interferometric fiber optic gyroscope, if there is no rotation, then you don't get an interference pattern. But then if there is a rotation, then you get an interference pattern. And the interesting thing about an interferometric fiber optic gyroscope is they're completely self-contained. They're usually a vacuum if it's like a ring laser gyroscope, or in fiber optic cables if it's an FOG. And there is nothing outside of the gyroscope that could alter the results that you get. And so the fact that you get this interference pattern that registers 15 degrees in 3 axes shows that the Earth is the thing that's moving, not any kind of outside influence.
Well, that's actually, that's relative. Like either Earth is moving or this is moving around Earth. That's actually the same thing. You cannot tell what the force is just by this. Actually, this is telling us that there is this sidereal rotation that I was talking about.
Yeah.
And
sorry, Karen.
No, that's just what I'm saying, that it does, it does not matter. Like everything is relative. I could even make up a universe that's based on my cat, and I could make everything go around my cat. And it would be very complicated, very, very hard. But like this is actually a very simple inversion. Either Earth is moving or the space is moving. And as in the space, I'm not saying that physical space is moving, but the ether.
Yeah. Now,
I don't know if that makes sense.
Yeah. Now, the big issue with that is that there is no way that an ether moving or electromagnetic field moving could affect what the gyroscope is seeing, because the function of a fiber optic gyroscope using the Sagnac effect is based on the speed of light in a vacuum. And the only thing that can cause the interference pattern is if it picks up a physical change in acceleration. So that's how we know that the Earth is physically moving rather than anything else. Oh God, did I delete the video?
Well, couldn't it be the space above Earth moving? Isn't it the same thing?
There's no way that space moving could affect because within the fiber optic gyroscope, the only thing that's changing is the fact that it's rotating physically changes the distance that one of the lights of path has to travel. And space changing wouldn't do this, because you can put these fiber optic gyroscopes anywhere on Earth. Every time an airplane boots up and they have 3 of these on board, the second they turn them on, they instantly get that 15-degree rotation in 3 axes. Now, let me just grab a video of mine quickly that I did have on here, but I seem to have got rid of it. Because another YouTuber called Wolfie6020, who's a pilot, took one of his fiber optic gyroscopes off of his drone and then put it onto a globe to kind of show what it actually picks up. Now, let me just find that video.
It would be very interesting. This is the 15-degree rotation is actually the sidereal rotation, right?
Yeah, well, it's the physical rotation of the Earth. It's the physical movement of Earth at 15 degrees per hour.
Something is moving 15 degrees per hour. I think it's actually relative if it's either Earth or the space above.
Okay, right.
How can
Here's the
we
video.
tell the difference?
Right. Now, let me just get this
the next
up.
Spider-Man
This is
scenario.
another one
Today
of
we're
my
gonna
earlier
look at a
videos.
flat earther that-
Now, in this video, they're talking about a fiber optic gyroscope that they got, and then here we go. So this is a fiber optic gyroscope from a drone, and then it's placed onto this globe, relative to his position on the globe, and he moves the globe backwards and forwards. And what it shows is that on the computer next to it, I'll show you in a sec, as the gyroscope on the globe moves backwards and forwards, it shows that rotation in 3 axes in the software, because that gyroscope is from a drone. So the computer thinks that the drone's doing that, and as you can see, as he moves the globe back round and round, it matches what he is doing with the drone, showing that a fiber optic gyroscope picks up a physical movement. It can't pick anything else up outside. It's literally showing you what the movement of what it is on is doing. So I think that's
Right.
a really good evidence that a gyroscope isn't picking up the movement of space or the ether. It's only picking up movement of what it is touching.
Well, I'm not too sure about that because, like I said, that's actually relative because the gyroscope is on the space. Like it should be able to pick up the movement around it. So either if it's Earth moving and bringing the gyroscope along, or if it's the space moving, bringing the gyroscope along, it does not tell the difference.
Now, here's the interesting thing about interferometric fiber optic gyroscopes is that they don't just pick up that rotation of 15 degrees in 3 axes. They can also pick up a 1 degree rotation around the sun in obviously one plane. And that should, I don't see how space could be moving in 15 degrees and also in another 1 degree in a large orbit. And the fact that a gyroscope of this nature picks up those movements shows that it's the physical movement of what is on that it's registering.
Well, yes, I totally understand what you're saying, but from what I've learned about this model, it's a symmetry. So the same way that the sun moves, also the sun is moving in this model, as everything is the same. So all of these little things, I actually find them the same thing because everything is relative. And I think the main argument is actually about the geometry of space, which would be either Euclidean or non-Euclidean. That's actually what the only place where I see a difference. But again, like I'm just fascinated by this model. I'm not an expert, but that's the only place where I see a difference. And I find it very interesting how everything can be explained this other way too. And we have coherence on what we have inside, like a cell, we have a nucleus, and it's like matryoshka, like one thing, how do you say? I just find it coherent. Like I understand what you're saying about gyroscopes picking up the difference, but I actually find it the same way. I will definitely research more into this, and I'm actually interferometer myself with my friends, and we're just trying to figure out stuff too,
Yeah, I think that interferometer gyroscopes are one of the strongest evidence for the heliocentric model. So yeah, I would definitely say look into that more. Okay, so what about something like gravity? How is that explained on your model?
Well, actually, this professor, he actually keeps it the same. What I'm actually really interested in is Morton Spear's electrostatic gravity, and he talks about gravity being due to a difference in the electrical potential. And what's interesting that he was able to actually get G, big G, just with a difference in potential. Morton Spears is his name.
Okay.
And what's interesting about this, that if we look at an atom, we see that the electrons have a negative charge, and atoms too, they follow a non-Euclidean space, because electrons, they occupy the more wider part, while the protons and neutrons are inside, and they're more dense and condensed. And here too we have the Earth having a negative charge, and the nucleus having a positive charge. And we see that as we go higher up, we have atmospheric, a difference in the electrical potential.
Okay, so
but that's actually my take on that.
My issue with that is that different materials would have different gravitational acceleration, because different materials would have a different, electrical potential, and a metal object would be attracted towards the ground more than a block of cement or something. So, and also we would float in a Faraday cage as well. If gravity was the result of electromagnetics, then Faraday cages, which block out electromagnetism, there wouldn't be any gravity inside them, and you would float inside of a Faraday cage.
Right. Well, no, it's not electromagnetism, it's electrostatic. It's a little bit different. And what was the first thing you said?
The different materials would have a different, acceleration.
Yes. Well, right. And well, that's actually due to the difference in the electrical potential. So right now we see that, like if I get a balloon and I rub it in my head, I will see a difference in the attractions with little objects, because there will be a lot of difference in the electrical potential. But Earth is huge. So the difference in the electrical potential from a metal object and a cement object is actually not even existent. You know what I'm saying? And actually, Morton Spears did an excellent job publishing. He even made a device that was able to attract to its surface anything, even electromagnetism, that could explain gravitational lensing. So his paper is very, very interesting, and he was not the only one that studied electrostatic gravity. And I find it also interesting, because atoms, like how do we get molecules? Atoms come together by electrostatic. So it would be a coherence from micro to macro.
Right. So the thing is, it's not just an attraction. There's a difference in acceleration. And, there would be a difference in acceleration. But what we find on Earth is that at different points on the planet, there is a different gravitational acceleration. So at the poles, there is a gravitational acceleration of 9.824 meters per second, whereas at the equator, it's about 9.78. And you actually weigh about 0.5% less at the equator than you do at the poles. And the reason for that is that the equatorial diameter is 26 miles more than the polar diameter, which means that you're closer to the center of mass. And also there is less centrifugal acceleration at the poles than there is at the equator, which would increase the gravitational acceleration. How is that explained on a concave model?
Well, actually, electrostatic and gravity are so very similar. If you actually go look up the formulas, you will notice there's also so many videos on YouTube that are amazed about how the formulas are
you're
basically
talking about
the
Coulomb's
same.
law, right?
I don't know that law, excuse me.
Well, it's, it's the law of like electromagnetism, and it is very similar to the universal law of gravitational attraction, because they both share the over squared distance ratio on them, but
right. So you just answered yourself.
Yeah, but again, the thing is that doesn't explain why there is this difference in gravitational acceleration at different points in the Earth. And it's not just at the poles and the equators that we notice this difference. If you are on a large mountain there is a slight increase in gravitational acceleration as well. Whenever there is more mass, you find there is a higher gravitational acceleration. If I could just show you a quick video.
Each of the two original.
Let me get to the right point.
Well, also, every mass has electrons. So every mass, as we have more mass, we also have more electrons. So it's actually, I also see a symmetry here because it will increase the electrical potential. If something like a mountain, we have more mass. As we have more mass, we also have more electrical potential.
What about objects that are like diamagnetic, like lead?
Yes, lead and what's that called? Yes. What about that?
Well, they would be
diamagnetism.
repelled.
No, that's not. Diamagnetism has nothing to do with electrostatic gravity. Electrostatic has the fields of line that are radial. Magnetism has curved fields of line. They're actually different fields. So it would not affect dimagnetics, paramagnetics, and ferromagnetics. They're just magnetics. And
so are you saying that they're on your model as well, that there is more mass at the poles than there is at the equator, and because for the electrostatic gravity thing to work, everything has to be exactly the same as it is on our model.
Yes. Yes.
But also inverted because of the way the electrostatic potential is calculated, and
the difference, yes.
Yeah, so let me just play this video for you a second.
First, we weigh a small lead pyramid to measure the force of attraction between it and the Earth. Its weight is 152.166 grams. Now we move the heavy lead ball under the scale, adding its mass to the mass of the Earth. The weight has increased by 1/1000th of a gram, which represents the attraction between the pyramid and the ball. When the mass under the pyramid got bigger, the force of attraction did too.
Okay, let me just get rid of that.
So if one thing that's very interesting about this experiment is that when something that has that is full of static, it will actually weigh less because in my model, because it will have less difference in the electrical potential from Earth and the sky. And this experiment as well, as you move the object over there, the object has mass, and every mass will have electrons. So again, we will be changing the difference in the electrical potential every time, because unless you're playing with just protons, you will not change the electrical potential because atoms have electrons.
Yeah, but when you have electrons that are you have atoms that are more stable, and the electrons, their electrical potential is different because they're closer to the nucleus or further away from the nucleus. And what we find is no matter the type of material, the gravitational acceleration doesn't change.
Mm-hmm. Yeah, that's because I said that.
All right, there's another video that's a really good one to show that there is actually a downward acceleration. This is a guy called Action Labs, right? And what he's done is, let me just change the speed so it's easier to see. So what we see is he's putting air into this bottle, and you see the bubbles going up. Okay, now as the bottle drops, which it will do in a second. Come on. Right, goes there. Right. So you see the bubbles going up, and as the bottle starts to drop, the bubbles stop moving, and it starts going to the side, and they actually become more spherical. And the reason for this is because gravity gets neutralized by the fact that the bottle is falling. The bottle is accelerating downwards at 9.8 meters per second squared, which means that the gravitational acceleration on the things inside is cancelled out by the fact that it's moving down. How is that explained by the fact that,
Well,
not only do the bubbles form more of a sphere, but they stop moving?
well, that's actually a little bit different because we're talking about an acceleration. So
Well, yeah, gravity is an acceleration.
Yes, so it's electrostatic gravity. So if we are talking about something accelerating upwards and something accelerating downwards, they're actually equaling out. So it has nothing to do with mass or electron. It has to do with equal acceleration. Equilibrium of acceleration. But what I would like to ask you then, why if I charge an object with static electricity, it will weigh less? Because the mass will not change, but it will weigh less.
Do you have any evidence of that? That something?
Well, you can Google that. You can be like, you can just write a static. Just Google it.
Right. So, I mean, there's many problems. Like someone points out, it's more articulate than I could have put it. The mass versus charge ratio of iron is 0.9% lower than for hydrogen. So the gravitational acceleration, if it's charge based, would be 0.9% difference. And we don't see that.
Based.
And thank you, Peter.
But it's not charge based, excuse me. It's not based on the charge. It's based on the difference of the electrical potential. So I could have something that has a zero charge, but it will still have a difference in a potential of something that has a one charge. Because it's not about the charge, it's about the difference. It's about the interaction.
Yeah, but then if we charged something, it would have a different gravitational acceleration, which we don't
That's
see
what
that.
yes. No, that's what I was telling you, that we actually do see it. Because if we have something with static electricity, it will weigh less.
That's something obviously I've actually never heard, so I'm trying to find. Oh yeah, of course. Now it would depend on the surroundings of things.
Well, that's up to you. Like up to me, that's up to because the difference of the potential is different. Again, this is all relative. So we do see a difference, and on you say that's because of the surround. On my point of view, it's because it's changed the difference in the electrical potential. So atoms have not changed. I don't know
if I put something above something else, then that would change the gravitational acceleration of something. So if I was to place a charged item above something else and then drop that thing, it should have a lower gravitational acceleration, but we don't see that. The gravitational acceleration is the same no matter what. Obviously, depending on where you are on the Earth.
If I charge a balloon and I try to drop something below the balloon, the object will actually go upwards and it will stick to the balloon.
Only if it has a charge potential equal to the balloon. But there's other things that kind of disprove that. Things like the Coriolis Force and especially the Earth Force show that if you have a... well, let's talk about the Earth Force because that's a very good one. So the Earth Force effect is... if there is a change in centrifugal acceleration, then you get a change in gravitational acceleration. So if you're in a plane traveling from east to west, you're going to have it weighing different than if a plane was traveling west to east. Because if you're traveling from west to east, you are increasing your centrifugal acceleration. So you decrease the gravitational acceleration. And if you're traveling east to west, you decrease the centrifugal acceleration, so you increase the gravitational acceleration. Wolfie again did an experiment where he took a 500-gram calibration weight, weighed it before he got on a plane traveling east to west and west to east, and then he weighed it while he was on the plane. And it showed that the planes that were traveling from west to east, the object weighed less when it was on the plane. So how is that explained with electrostatics?
Well, again, we are talking about centrifugal force. So we are using Earth's rotation here.
Yeah.
And in my model, we are using the celestial sphere, well, the space rotation. So again, I see symmetry here because either the Earth's rotating or the sky's rotating. We're still talking about rotation, and we're using a centrifugal force. So it's not about the mass, it's about a centrifugal force
But
here.
how would the centrifugal force affect electrostatics? It doesn't make sense that that would affect the gravitational acceleration.
It's not affecting the electrostatic just the same way it's not affecting the mass. You're actually using...
But what you are doing is you are literally reducing the gravitational acceleration because you're acting in the opposite direction with a centrifugal force. Whereas I don't see how that makes sense if you're saying gravity is an electrostatic phenomenon.
Well, gravity has the fields, the lines of force. They're actually radial, so they're not. They don't follow a rotation. So they're just as electrostatic gravity that are radial. We're talking about the same lines of force, and so I don't see how there is a difference here. Like gravity is not affected. Gravity does not make. How do you say? It's not gravity that gives us the centrifugal force. It's the rotation.
Yeah, but that's my point. Is that if you increase the centrifugal acceleration, you decrease the perceived gravitational acceleration. And I don't see how a change in centrifugal acceleration would alter a electrostatic force.
I guess the same way. I'm having trouble to understand how it affects mass.
It doesn't affect the mass, but it makes the mass weigh less because obviously weight is mass times the gravitational acceleration. So if you are adding centrifugal acceleration, you are reducing the gravitational acceleration. So the g in the equation of weight becomes less, meaning an object will weigh less.
So because we get the g with the electrostatic gravity, we still get g with electrostatic gravity. So I assume it would be the same. Like, I'm not an expert, but I see two forces that are acting the same because they both have fields of lines that are radial, and they both use basically the same formula. And then we see centrifugal force. So I'm actually seeing, like, if we're not giving the names of a force and we're just looking at the lines of forces and how they act, they're actually the same. Like if we're just looking at the lines of forces and the square distance formula, like without naming, it's about mass, it's about electrostatic potential, but just looking at how it works, I see the same thing.
Right. Now, one of the things also is you're talking about electrostatics, you're talking about Coulomb's law, which is the equation that is similar to the universal law of gravitation. And the thing about that equation is that it also requires a distance to a center. And when the vectors all point downwards towards the center of the Earth, they don't point upwards towards a celestial sphere.
Absolutely.
What you're suggesting almost means that gravity would be pushing you down rather than pulling you down, right?
Yes.
But that doesn't make sense with the bottle that I showed you. There's no reason why the gravitational acceleration would change when the bottle is falling if it's kind of a pushing force coming from from above rather.
Because the pull, because the acceleration, there's two different accelerations. So like I said before, water, because air, of course, is less dense and goes up. So it would just equal the two accelerations. Like I see everything as very relative. Again, like I could make a universe based on my house, and that would be possible, and the math would work. It would be very, very
I mean,
complicated.
I'd love to see the math for that, because I've heard people say things like that before. But I had a flat earther say to me, "Oh, maths can do anything. I can show you maths that could show an elephant can balance on his trunk." Well, my answer is, show me that math. I'd love to see the math.
Well, I can show you the math on concave. This math, the math about the universe going around my house would be very, very complicated, because it would not be linear math. It would not, everything would be very, very complicated. On the concave math, I can definitely show you that, because, you know, I follow a mathematician that made 2 books on this model. So I got all the math you need on that.
I'd love to read those books. That would be quite interesting.
I will definitely link them to you.
Okay, great.
His first book is in Italian, and his second book is translated in English. And so
let me talk about other things rather than gravity and that then, because you seem to be explaining it away with relativity, but I don't think you're quite getting relativity right. But let's stick with empirical evidence, right? Things like physical measurements, things like bridges, the Van Hines Narrow Bridge in New York. Okay, the pillars on that bridge are completely level, but the tops are 1 5/8 inches further apart than the bottom. Even though they are completely plumb and level, they have a difference in the distance between them at the top and the bottom. And that shows a convex rather than a concave. So how is things like that explained?
Well, I actually introduced that a little bit earlier when we started this chat, and it's about how the non-Euclidean geometry deforms space. So the higher you go up, the closer you get to the nucleus of Earth, which would be the center of the celestial sphere, there is much more deformation. So that's what I'm trying to say, that this model is so fascinating because there is no way to tell the difference. This is what the mathematician is saying, because that's just how
that would mean that distances are different as you go up, and we don't see that in planes. I mean, a plane still has to travel the same distance.
Well,
it's not reduced based on the altitude.
We actually do. Is that we think we live in a convex world. So the deformation of space is when we flip the world inside out, and then we see and then we use non-Euclidean geometry. With non-Euclidean geometry, then the higher you go, the more deformed space gets. When we are outside of the world, we use Euclidean geometry, and we still get the same difference, the same distances, because one word uses Euclidean geometry and the other uses non-Euclidean geometry. And it's actually a very easy inversion. It's not very complicated. It's just inverting space. And with this inversion, if you like to see the picture I sent you earlier, this is how I got the Fibonacci double spiral, which is the same thing we see under the ferrule cell. Yes, absolutely. And I find it very interesting, because why would I get this image from the formula of the inversion from non-Euclidean space to from a Euclidean space to a non-Euclidean space? Of course, this is not proof, but this makes the model very, very fascinating, because we see this only in nature. So why am I seeing this if that's not nature?
Well, because the Fibonacci sequence pops up everywhere. It's kind of a natural way for things to exist. I don't think it gives evidence to a model in any way. But we can keep talking about physical measurements. One of the favorite ones that I use is LIGO. The massive interferometers. There's 2 of them in America, 1 in China. There's a few more around the world. And
we have 1 in Italy too.
Yeah, and now when you're talking about the ones in America, one of them especially, the Langford one, I think, is literally built next to a river, a level water river, and at the end of the 4 kilometer arm, it was over a meter above the surface, and they had to use precision pouring of cement to to keep it so that the laser inside the vacuum tube could be completely straight. And it showed that the Earth fell away from the a tangent line, because if the Earth was concave, then it would have gone up onto the tangent line. But we actually see the physical measurements, and it's the other way round.
Well, this is just the same argument. This is what non-Euclidean geometry is about. Like when we invert a sphere and put it inside out using a non-Euclidean space, this is actually what we get. We get the same thing as we would get in a convex sphere. And that's why they're symmetrical, because there's no physical evidence. And you mentioned those big interferometers, and we have one in Italy too. It's called Virgo. Yeah. And what I found interesting about the interferometer is not actually how they made it, because non-Euclidean geometry really explains how we get the same results. But I find very interesting that to get zero fringes, they have to use so many different types of corrections. So it's like, if light does not have an anisotropy, then why are we using 3 different types of methods to keep the light beam straight? So we're trying to do our best not to measure those fringes.
Well, yeah, that's why I'm talking about physical measurements. And
yes.
I mean, and it's a physical thing. It's not just an inversion of light. It was actually a physical falling away of the Earth from the tangent line. And that could only happen on a convex Earth.
Well, only if you keep a Euclidean geometry for concave as well. Maybe you're not understanding non-Euclidean geometry well, because it's not a geometry that we're used to, because we usually
I use
Euclidean geometry
a lot, but that still doesn't explain how we physically measure a drop away from the tangent line. Non-Euclidean geometry, it allows us to calculate things in curves and everything, but it doesn't explain how a concave Earth would appear as a convex Earth with a physical measurement of something. If the Earth was concave, the end of those 4-kilometer arms would be burrowing a meter into the ground.
Okay, so the thing is that if we go lower, the deformation of space is based on how far you are from the nucleus, just like we see with everything in nature. The closer you get to the nucleus, the denser the geometry gets. So again, here we have this symmetry. And actually, Amico Roxas made a lot of drawings, and he, as he was a mathematician, he used to really spend time drawing things out and explaining why the 2 geometries are exactly the same. And I'm not a mathematician, but I've read his books. And
could you just put that drawing up again, if you don't mind?
Yes, absolutely.
Yeah, so everyone can see that. Just explain to us what that shows.
Well, that's non-Euclidean geometry. That's the 2 different spaces, and that's the Euclidean geometry. It's just showing the different deformation of space, how the lines, the tangents work. Right.
I mean, so what you're saying is that no matter what, the Earth is going to appear convex, even though it's concave.
This is what this guy says, and it makes a lot of sense to me. I started studying a little bit of non-Euclidean geometry, and it's starting to make a lot of sense to me. And so this is what makes this model, to me, very fascinating. The fact that the only way that we can tell which model is right by measuring the light speed anisotropy and keeping on researching on that.
Okay, right. So I guess we need to move to things like space agencies and what we see from them.
Yes.
Why do all space agencies show the same thing? Are they all just lying to us?
No, absolutely. Because that's because light curves. In my model, light does not go straight. So if light is curving, then you will always see a circle of Earth, even if it's concave and you're going far away. And also, Amico Roxas made he made a lot of drawings on that too, on how Earth looks from space, because that's actually a good question, like why are we not seeing it concave? But if we imagine how light is curving, the farther you go up, you're always going to see a sphere. You're always going to see a circle, not a sphere, you know?
I mean, that really doesn't make sense to me. Like, let's just look at this image, 1972 blue marble. You can clearly see the shape of the Earth, and there's blackness all around it. Surely, if the Earth was concave, then you wouldn't get this very clear sphere in a sea of black. I honestly don't understand how that can be construed as being concave. It just doesn't make any sense to me.
Well, I will be very happy to first of all send you the books of somebody that is much better than me at explaining how light works if it curves. And to me, actually, because I started out as a flat earther, so when I see some images like, oh my God, is this a real image or is this not a real image? You know what I'm saying? But I'm still debating on whether these are real images or not. But Amico Roxas believes in these images, and he explains them with geometry and math, and he's just saying it's the curvature of light. I'm sure it's not easy to understand.
Why does light curve though in your model?
Because everything curves here on Earth. Tell me something that does not curve, like anything, like that's the expression of
the
nature.
laser inside a LIGO,
that's not nature. Like, I'm talking about nature. The laser inside the LIGO only goes straight because they use 3 different types of methods to keep it straight. Otherwise, it would curve as well. And that's why we have this light speed anisotropy that Dayton Miller talked about, Roland DeWitt found, and Cahill found, and I hope to find it too one day.
Okay, sorry, one sec. I'm just getting rid of a troll in the chat. Bear with me. Sorry, one sec. Hide user on this channel. There we go. Right, sorry. Okay, so what about orbits of satellites? Let's look at geostationary orbits, which have to be in a particular place, exactly 26,260 odd miles above the equator, and that's where all satellite TV satellites are placed. And how is something like that, where the physics of orbital mechanics is very well understood, how does something orbit on the inside of a sphere?
Well, instead of orbiting Earth, it would orbit the celestial sphere.
But why? Because an orbit in our model is something in free fall towards the Earth, okay? The ISS is in free fall towards the Earth. It is falling towards the Earth all the time. But because it's traveling 17,000 miles an hour, it constantly misses the Earth and keeps going around. So how does an orbit work on the inside of a hollow sphere? I don't understand that.
Well, you're bringing up good questions. I'm actually not very prepared on this, but I assume that it's as we said before, that gravity has the same fields of lines as electrostatic gravity. I would assume that it would work out that way too. And again, I know as a flat earther that too, I used to be like, oh my God, satellites don't exist. And now I do, of course, believe they exist because I've seen them and all the other things. But sometimes the very faraway satellites, I keep questioning myself, and I know there's evidence that they work, that they're there, but maybe they're closer to us. I don't know. I'm actually not an expert on satellites and all the whole space. I really just studied the geometry. I studied a lot the light, how light moves and it works. And I am sure that you have many things that you understand much better, because actually concave Earth is not very known. So I've only known one mathematician that talked about it, while on the heliocentric model there's been so many great minds that have helped figure out everything about it. So I am sure I do not have all the answers up on a concave model, but on the same hand, I am sure that this model can work, because the math works. And at the same time, I find it very fascinating being inside Mother Earth, and I find it that it has a lot of philosophical sense as well, not just on the math.
I mean, philosophy and stuff I don't really go into, because I like to work with empirical evidence. I like to be able to physically back up my claims with actual physical real world observations. And from what I'm getting from you is that no matter what we see, it's just inverted. And even though it looks curved, even though it physically measures as curved, it's still concave. And I feel like it's a little bit of a cop-out, because you can't really explain away physical measurements, physical dropping away of the Earth in LIGO. These things don't match a concave reality unless we really aren't seeing what is really there. But I mean, if you look at, again, this image, the 1972 blue marble that was taken with a physical camera, a Hasselblad 80mm camera, I think, right? There's nothing between the Earth and the camera, so the light is literally just going straight. It's bouncing coming from the sun, bouncing off the Earth and going into the aperture of the camera. There's nothing in between there that would cause the light to alter, to make it look different, because obviously space is a vacuum. There's no medium, there's no reason for the light to bend. So why if they were like 2/3 of the way to the moon, why would it show that? I mean,
because light in the concave model is not bending because of something. Light in the concave model is bending because of its nature, because it's not a radial illumination, it's a cardioid light illumination. So it bends because it takes the shape of a field.
The nature of light, though, is to go straight. This is kind of a fact of physics, and LIGO shows that the laser goes completely straight. They had to, 20 years it took to calibrate LIGO to make sure that it was going completely straight, and that it was pointing in the right way. The nature of light is to travel in a straight line, unless there is a change in the density of medium that is causing it to refract, and then it can bend. Or a large gravitational mass can bend light. We see obviously light bending around black holes, and they use the light coming around from behind Mercury to kind of confirm Einstein's predictions around general relativity and stuff. And all the predictions around general relativity work out, and none of general relativity and special relativity is compatible with what you're saying.
Well, special relativity is not compatible with this light speed anisotropy found in the interferometers either. So I keep finding...
I would disagree.
Yeah.
I mean, it makes perfect sense when you look at the results of Michelson Morley's experiments. If you're kind of basing it on classical mechanics, it doesn't make sense. But then if you look at it through the lens of special relativity, it absolutely makes sense.
Right. Well, again, special relativity says that light should be not stable. How do you say? it should have the same speed throughout 4 directions. So if we see an anisotropy in a direction and this anisotropy has a cycle, that's not predicted by special relativity, actually.
So I would disagree with that. As far as I'm aware, all the observations of light match special relativity completely. Especially more and more recently, we are discovering more and more things that back up Einstein's predictions around relativity. Recently, they discovered a neutron star that's literally churning up space-time so violently that it warps light in so many different ways, but it all matches completely the predictions from Einstein's calculations.
Right. Well, I really enjoy Einstein's work. I really do. So I'm not saying that it's wrong. Absolutely. Like I said before, what we have from data, we get the result from data, and data is a fact no matter what. Then the theory that comes along can be different, and it does not change what we actually measure. So I really admire everything that all of Einstein's work, especially like how he was able to combine space and time that are of course very, very well strict, close. How do you say? They're very close together. But again, this is just a different view of the world, and I can understand how you're like, no, for me it's not working. But if we look at it from another view, it's all relative, so it actually works. And again, from what I'm learning, from what I've learned from this guy, that I will never be able to tell the difference. So what I'm left with is being fascinated by it.
Okay. Now, the thing about the heliocentric model is that it can explain all the observations we see. It can explain satellites, it can explain orbital mechanics, it can explain special and general relativity, it can explain why the light bends in the way that it does, it can explain the redshift in galaxies. It all matches the heliocentric model. Yet with concave, you have to kind of change things a lot, especially with things like orbital mechanics. And I think that's one of the things I'm going to stick to here, is that I don't think there's any way that satellites could work on a concave Earth, because they've got nothing to miss. Like I said, an orbit is literally a free fall around something, but with a tangential velocity that's enough so it misses it. And I just don't think there's any explanation for how orbits work on a concave Earth. Like how does the moon work on a concave Earth? Do you believe we landed on the moon?
No, I don't believe we landed on the moon.
Okay.
But about the orbits, there's actually some really good graphics that are done by a channel on YouTube. It's called Reality Analyst, and he did some very, very amazing graphics. And what I find interesting is the
Was that Reality
zodiacal
Analyst,
light.
did you say?
Yes.
Okay.
About so you're not going to find this on his channel. You're going to find some good animations. What I wanted to talk about is zodiacal lights and Gegenschein, which is the light right on the opposite side of the sun. And with concave orbits, how the sun is orbiting around the celestial sphere, then we actually see a coherence on why we see zodiacal lights only on spring and autumn, just as well as the Gegenschein, which is mainly visible during the same season, is of the sun is actually becoming parallel. Otherwise, because it's an inversion, the tilt of the Earth is actually the tilt of the sun. So everything is inverted. So we have the orbit of the sun, the tilt of the sun that during equinoxes is leveled. And so we have some observations that we can do on our sky, like the zodiacal lights and the Gegenschein, that are mainly seeable during spring and autumn. And in the heliocentric model, there is actually no connection on why during spring and autumn we're able to see these things, because they're in the heliocentric model, they are due to an asteroid belt. And they should be able to be seen when we're actually closer to either closer or further away to the sun, either in summer or in winter. I'm not too sure, but if you look up zodiacal lights, and if you look up the asteroid belt, and you will just start to question, why are we only seeing it during spring and autumn?
Now, saying spring and autumn seasons brings up another issue, because of the tilt of the Earth is the reason we have the seasons. So obviously,
yes,
when in the northern hemisphere, when the tilt is away from the sun, the light has to cover more of an area, the same amount of energy over a larger area, so we get less energy and it's colder, and vice versa. How does that work on a concave Earth? What is the reason for the seasons?
Because we have instead of being the inclination of Earth, it's the inclination of the sun, and that's how we have the seasons.
Right, but that doesn't
Basically,
make sense, because
that
that would mean that the sun was putting out different amount of energies based on
No.
its tilt, whereas
No.
the sun is a sphere. It's radiating energy in all directions. The axial tilt of the sun wouldn't change the amount of energy that certain areas of the Earth receive.
But it's not changing the tilt. Like Earth is not changing the tilt during the year. It's just changing the way it's the inclination towards the sun. It's always It will always be inclined the same, just as the sun will always be inclined the same. It will just move along.
But my point is that, so for half of the year, the northern hemisphere is tilting away from the sun. For the other half of the year, it's tilting towards the sun because of the orbit. And that means that different areas of the Earth receive different amount of energy at different points of the year. So if you're saying it's the tilt of the sun, that doesn't explain how different areas of the Earth are receiving different amounts of energy.
Well, if I have a flashlight and I tilt it more towards, and I have like a concave bowl, and if I point it upwards, and of course I'm going to have more energy here than on the bottom.
But if the sun is the thing that's giving us the energy, though, and it's kind of in the middle of the, it's part of the celestial sphere in the middle of the
it's not in the middle, because we're actually in the whole galaxy gets inverted, so it's actually very close to us compared to the middle of the celestial sphere, because remember, the distances stay the same. So in the middle of the celestial sphere, we cannot have the sun, because the sun is in our solar system.
Well, how do we receive? How is it that all sunlight rays appear parallel then?
Because that's the inversion of light, and that's like all the work of this mathematician, and that's like from the same formula that I got the double Fibonacci with Python, and the curvature of light, like I said before, you will not be able to tell the difference if light goes straight or if it curves, because the angles at which it hits your eye will not change. So if the angle at which the light will hit your eye does not change, the position of the object does not change. So in either ways, we will find the same rays. And Roxas made some beautiful illustrations on this.
The thing is, though, you said it's the inversion of light. A straight line can't be inverted. An inverted straight line is still a straight line.
Well, because it's the inversion from a Euclidean space to a non-Euclidean space. And the inversion of a straight line will not ever get inverted, like you said, because a straight line is a very, very particular geometry, and it's very, very strict. And why are we still using this strict geometry while we see in nature nothing is using straight lines? That's actually another point on why it should be curved.
But that's my point. We see the light from the sun as parallel rays. There is no inversion. It's a straight line that comes towards us because
right.
in our model the sun is so much larger than the Earth that we get that.
We will never. Sorry to interrupt you,
right,
but we will never be able to see the difference. That's just how the inversion works. So we will get parallel.
Why wouldn't we be able to see the difference?
Because the distances don't change, because the distortion of space make it so that it is very, very far away, and the way light hits, it will still make us see parallel lines.
Okay.
The distances stay the same, so that will not change.
I just still don't see how that shows us that sun rays are parallel, but there's other things as well, like the shadow of the moon being a lot smaller than the actual moon. How would that be possible?
Because the moon is closer. I wanted to show you. This is the eclipses on the model.
Let me just get your
the shadow of the moon.
Okay, could you just explain that to us, please?
Well, this is just the inversion, and that's the moon, and that's making the cone of the shadow. I don't know if...
Yeah, I see it.
You see it?
Yeah.
Because it does not look in the center. Okay, so that's just the moon, and it's making the shadow, and that would be the sun. And these are the two eclipses explained in the concave model.
Right, so for that we have to assume that light never travels in a straight line.
No, that's what this whole model is about. It's about light looking like it travels in a straight line, but it actually does not.
Right.
It seems crazy, but
there's so many more things that we can talk about that doesn't make sense on a concave Earth. Other forces, like what creates lava on a concave Earth. Things like volcanoes are perfectly explained on our model, but how is there a hot lava underneath us on a concave Earth? What's causing that to be there?
Well, I actually don't know, and I've never got into that, and I wouldn't know how to answer you, so I'm not gonna try to make stuff up, and surely I'll look up, I'll start researching, because there is many things that could give me answers, but I'm not just gonna guess an answer.
I appreciate that. Flat earthers tend to just make up shit, but okay, what about celestial observations then? How are things like redshift of galaxies and the ability to measure the distance of stars based on parallax and everything, how does that all make sense on a concave Earth? Because I want to show you some observations that a friend of mine has made, a guy called Geistview. He uses this telescope with a camera attached to it, and he gets the most amazing images of space. Things like this, and things like this. You can see the Horsehead Nebula there and everything. And how does observations like this make sense? And the fact that we can analyze the stars with spectroscopy, and that can tell us how far away they are and things like that. How does that all make sense on a concave Earth with the celestial sphere in the middle?
Well, again, like distances stay the same, switching geometries. So, these galaxies can be very, very far, even though the space is very, very small, because there is a deformation of that. I think it's actually square to the distance of of to the ground. It's actually a very simple formula, and so again, we would see all these beautiful galaxies, and some concavers in here in Italy, they actually believe in aliens and that there's actually other worlds up in the sky, because
So
it all
what's
could be
okay?
possible,
What's
assuming the
causing
deformation of
the
space.
what's causing that deformation? What is causing space to, it'd have to be physically compressed relative to us for that to be the case. What's the physical mechanics behind that?
It would just the physical mechanics that it's not a physical mechanic, it's just how the geometry works. Like um, if we take an apple or if we take an orange, like what makes this seed have that physical geometry in respect to the rest? It's
DNA.
just the non-Euclidean structure of the world that make it have that deformation.
Um, I
And
don't,
then you got redshift
yeah, I
and
still don't understand why space would be like so. Okay, do you believe that we can go into space?
well, me personally, I don't, but I'm just a girl, this mathematician, he did believe, of course, that we went to the moon and we went to space and everything. My personal opinion that is that we don't. But that's just my personal opinion on this.
What do you base that opinion on?
Well, I actually base it on the Poincaré disk. You know how the deformation, it's like, I always make this poem. Can you put, if you have two notebooks and one with big squares and one with little squares, and you color one of the little squares with a color, and then can you put third square, this colored small square in the big square? And you'd think that you could, but then again, if you put the little square in the bigger square, then it will get dispersed. I don't know if I was able to explain myself, but to me, it's kind of like you cannot go so much up higher, because if we see how a Poincaré disk actually looks like, it's like we have the same geometry, it's like fractal geometry, the same exact geometry, but at different sizes. So to me, it's like, I don't know. It's like we can't go there because it is the same geometry, but not our size. But that's just my personal opinion, and don't have any math to back this up.
Okay. Right. We have a few questions from the audience for you, if that's okay. I'll just go through the super chats and we'll ask you the questions. First of all, I'll say welcome to the new members to the channel. We've got Bandit, we've got Richard Kitt, Fargoth, NA. Thank you guys very much. It obviously means a lot. I literally couldn't do this without your support with super chats and memberships. So thank you very much. Okay, John Rapp for $5 asks, how can we possibly see less than 180 degrees north, south, and east, west, and all opposite angles between inside of a sphere?
I'd ask, could you repeat that question? I didn't get that.
How can we possibly see... Is that... How can we possibly see greater than 180 degrees north to south and east to west, and all opposite angles in between inside of a sphere? I think he's asking how can we see so much of it if we're inside of a sphere.
I don't know if I'm getting the question.
John, could you please just clarify that question a bit in the chat if you don't mind? We'll get on to some other ones. Justinian for
Sorry.
$5 says, can you ask her what the symmetries of a Lie group matrix of SU11? She spoke of isometry and symmetry, but she doesn't know Lie group matrices.
No, I don't know. I don't even know what this question means. I'm actually not.
Matrix maths, I think.
I'm not as like seriously. I've read a lot of books, but I'm not physics. I'm not. How do you say it? I'm not.
It's okay.
I don't know a lot of things.
Okay, right.
That's
So,
what I'm trying to say. That I'm studying this model and I find it very fascinating. And but I don't know all the answers, and I am not I don't have a physics degree, so like that question to me, it's like gibberish.
right. So, Jonathan L for $2 asks, can you explain seismology and earthquakes? The fact that let me get an image up to demonstrate
Yes.
what he's talking about there. Thanks to Conspiracy Cats, I've got a good one. Let me just find it. Sorry, one sec. Oh God, why is there so many? Sorry, one sec. Maybe it's before that. Ah, here we go. Right, so when you get an earthquake on the sphere, you get P and S waves, and you get the P wave shadow zones, which obviously where the waves can't travel through, and you can literally pinpoint where the epicenter of earthquakes are based on the P and S waves. How are things like this explained on a concave Earth?
Well, I could probably invert this image with a Python and tell you exactly how we would get it, because again, because it's an inversion, everything that has to do with space, it's just inverted. So I would have to invert it with Python to tell you exactly how where we would get it from. And you're probably thinking we do not have a nucleus inside, but we're actually not measuring it from that far down when we get the earthquake.
But that's what the PNS waves and everything can tell us. They can tell us, exactly where on the sphere they're coming from. They can tell us the depth of the epicenter, and it all
Right.
matches what we expect to be the case.
But this is actually they're not that close to the nucleus of Earth, of course. That we know, that we can tell, because seismic waves are not coming that close to the nucleus of Earth.
Okay, right. Let me get back to the questions. Copernicus Thinker for $2 asks why southern observers cannot see Polaris.
Well, because there's a celestial sphere. A sphere, you will never be able to see two sides of a sphere.
I suppose
at
that
the same
on
time.
a concave Earth, that question does make sense. So, yeah. I'll just read the other ones that weren't really directed towards you. Bear with me if some of them are mean. Some people can be mean.
Yeah, read me the good questions, or the easy questions. Come on.
Dan Robinson for £10 says, why do people feel the need to believe in all this bollocks? Is it a fear of reality or plain stupidity? It's sad to see nice people at Israeli demonstrating such ignorance of reality. You don't need to answer that one, don't worry. JL Warren for $1.99 says she understands non-Euclidean like Lovecraft did. And Curtis Reynolds for $5 says, holy Jesus, this chick makes me non-Euclidean dizzy. And Cajun Crustacean for $5 says, this isn't your average stupid, this is advanced stupid. Well, yeah, like I said, some of them can be quite mean towards the guests, but this is a different conversation, okay? When I have conversations with flat earthers, it's all based around a complete and utter ignorance of science. Whereas you are talking about a lot of science that does make sense. I think that the inversion stuff doesn't really work in the way that you're describing. I'd love to read the maths book that you were talking about so I can talk a bit more on that. But the things like orbits are one of the biggest issue that I see for a concave Earth. I don't understand why there would be an orbit on a concave Earth. That literally doesn't make sense to me. Hey team, and I've sent you a link if you want to jump in, buddy. Now let me get back to. So if we, any observation I show you, you're just going to say it's because light is inverted, really. Like on this observation, we can see the camera height's 210 meters. The top of those bridges is 210 meters, but those hills in the distance are over 500 meters, which means that they're falling away. But your answer to that is that it's all inverted, right?
Yes, yes.
Okay.
It's that's, I don't know if you can see this, but if light curves and so does Earth, then we have the same, we expect to see the same observation.
Okay. I mean, I suppose my one of my largest points of contention with this is the nature of light is to travel in a straight line, whereas you're asserting that the nature of light is to bend. So it's a kind of a major disconnect there that I think we're not getting around.
Yes.
I really don't think light naturally bends. I think the nature of light, well, I don't think I know based on physics, the nature of light is to travel in a straight line unless there is something causing it to bend, like gravity or refraction or something. But you are asserting that light naturally follows a curve, right?
Yes, that's what this theory is all about. It's about applying the curvature we see in nature to light as well, to electromagnetic propagations as well. So this is the whole point of this model, is that light follows a curve, and this curve is not just any curve. This curve follows the golden ratio and all that stuff, and I can understand where you're coming from, because that's where I came from as well. But after reading this book and after researching, I just finding this model interesting, and after I found that image on the inversion of light, I just keep it finding even more interesting. And again, if light goes straight or if light follows a curve, we cannot tell the difference. We cannot tell the difference. Yeah.
Where's that echo coming from? Where's that echo coming from?
That's.
Oh, it's team.
That's me. Hold on. I told you I forgot that setting had changed. I'm sorry. Give me 1 second to fix it.
Okay. Elefaki, this is my partner in crime, Team Skeptic. He knows a lot more about some of the physics than I do. Team, have you been listening? Oh, he's gone away completely now.
No, I'm sorry. I just literally walked in the door and turned on the thing. I just got home.
Okay, how you doing? Everything all right?
Hi.
Yeah, everything's fine.
All right, team. This is
Hi, how are you?
Elefaki. So, right, the main point that she is making is that light naturally curves. Can you talk a bit about that?
I mean, it doesn't.
Okay.
What are the physics behind light naturally curving?
Okay, so what this model is actually saying is that we actually cannot tell the difference between a curved path of light and a straight path of light, because the angles do not change. And since the position of an object is, we can tell the position of the object by the angles at which light will come through our eyes. With applying the transformation done by Paolo Emilio Amico Roxas, which is actually a very simple transformation, inversion from a Euclidean space to a non-Euclidean space, then we will see that the angles will change, and so the object will stay the same, and we will not be able to tell if light traveled in a curve or in a straight line.
Okay. But, I mean, when you're talking about a transformation, okay, so you're talking about a way of looking at things, okay, a convention, a type of convention. What you're not doing is you're not explaining the physics behind why the light naturally curves. Like if I, let's say, hold on, give me 1 second. Let's say I was to turn over on my head, would the light look like it came from a different position?
Absolutely
Simply
not.
because I changed my orientation?
Wait, I didn't get the question.
Because it should be, it should, okay, like when you say light naturally curves on its own, let's say we're in the middle of space, okay? No gravity, no nothing. We're in the middle of space, and we have a laser. And we shoot the laser in a straight line. What you're saying is that the laser would naturally make a curved path, correct?
Well, we will never be able to tell if the laser is actually going straight or if the laser is curving. That's what I'm trying to say. That's what this mathematician
Okay, well,
wrote
I understand that. I understand that. But transformations aren't about our perceptions. Transformations are actually about the physics, okay? So you would have to explain how your transformation ended up changing the physics of light, because we understand light pretty well, okay? So what you're doing now is suggesting a new form of physics to explain electromagnetic radiation.
Yes, not me. This is actually done by Paolo Emilio Micoroxas, which was an Italian university professor, mathematician, and he wrote 2 books on non-Euclidean space and the curvature of light. Me, I'm just a girl, and I came over here because I actually thought I was going to debate on flat earther. So I was like, yeah, bring it on. And then he was like, I'm not a flat earther.
God no.
So, yeah, I'm actually just.
Well, okay. So when let me get back to my let me just point out to you, clarify my question a little bit better, so that maybe you can research the answer a little bit better. Okay. So let's say you were in space and you shot a laser out and there was no massive body to deflect the laser or anything like that. Okay. Now, if you have a detector, let's say you wanted to set up a detector to detect this light, and you set up your experiment, you would set up the detector to measure the light being straight. You know, you wouldn't, if you had to account for the light being curved, then you would say, okay, well, if I want this detector to catch this photon of light, then I need to adjust for the curve. I need to adjust for which way the laser is going to bend or the light is going to bend naturally. And so you would set your experiment up that way, and you'd be able to prove that light bends on its own without the, we're saying minus the influence of gravity, so we don't have to worry about talking about light following a curved path around a massive body in space. Now we're just talking about in the middle of nowhere, in the middle of space, no gravitational bodies. Light, according to our understanding of physics, light is going to take a straight path from one point to the next. It's not going to curve. That would violate the action of least principle. Or the principle of least action, I'm sorry. I'm really tired.
Right. I am too. Here in Italy, it's like almost 2 at night. And
well, we'll go for about 10 more minutes, and then we'll start wrapping up, guys, just so everyone knows.
Yeah, because we actually just talked about all this, and like I said before, I will be very happy to send you the link. So on the curvature of light, you're like, why would it curve? And what this mathematician says, that light curve just like a magnetic field curves, and it would curve because everything else in nature curves. And we actually talked about this all night, and then, but ruler is not made by nature.
Straight.
It's made. Oh, that's right. Don't.
Okay, hold on. Okay, hold on. But I can pull up. I can't think of the formations that they're called, but they form natural hexagonal shapes, and they're based on the pressures. The pressure you'll find them in like volcanic the volcanic stems that run up and straight up and down. Because there's a high amount of pressure, as it cools, the pressure radiates outwards in from a center point. So it actually makes fairly straight lines, hexagonal shapes in rock. These are natural formations. So not everything in nature
So,
curves. There are
right.
things
So
in
this seems
nature. Go ahead.
absolutely. This seems like a very particular um, type of situation that lets us have a straight line. While light is not very particular, we see light. Light is everything we actually see, and light, it's electromagnetism, which we, of course, we know that comes from magnetism and electrostatic, and radio lines and curved magnetic lines. So he actually has a point on this, and I find it very interesting. And maybe he wants. I also found an image I got with Python using his transformation, which I got the double Fibonacci spiral, which I find very fascinating. Of course, it's not proof of what I'm saying, but it makes this model very interesting because why am I getting the Fibonacci spiral from the curvature of light if the Fibonacci spiral is actually an imprint of nature, of nature's way of expressing itself? I don't know
Have
if
you
I
ever
was able
thought that
to make you.
maybe the mathematics of the transformation are, inclined
Yes,
to come out to the Fibonacci sequence? I mean, if that's the case, then the answer is in the mathematics,
I
not in the nature of
I would
light.
love. I'm actually looking for a mathematician that will help me tell me why am I getting the Fibonacci. So if you guys know in the math, I would love to find out why. Like, I'm not saying it's the only option that the Earth is concave, but I
Yeah.
am seeing that it is so very fascinating finding the double Fibonacci spiral in a simple transformation, no doubt.
Okay. Well, I mean, you can find evidence of the Fibonacci sequence in a lot of different natural events. So, I mean, just
Only
applying math
natural.
to natural events. Well,
No, no, no.
yeah, but you could also
Can
make
you?
them unnatural. We could mathematically recreate the Fibonacci sequence at different like at different intervals. For instance, like we could
Right,
take the Fibonacci sequence and multiply it by 2, and it's still a mathematical sequence that's still a version of the
right.
Fibonacci spiral.
Can you show him the picture fight?
Yes. This one. Is that the right one?
I can't see it.
Oh. Well, it's the first one that you sent me.
Yeah, either that or
Are you
yeah,
talking about
that's
the
fine.
ferromagnetic light?
Well, no, that's actually the ferrocell, and I'm not. But it's the same thing I got. See the
Oh,
on
ferrocell,
your
yeah.
left side. On your left side, you will see the picture that says inversione. That's the picture I got with the inversion, and it's the same as we see under the ferrocell.
Yeah, you created that in
And
Python. You said, yeah.
Yeah, well, I mean, again, if you math, it can come out with beautiful pictures, and you can take one
absolutely,
equation and apply another, or multiply it by another equation, and it'll give you a graph that has a picture look very ordered to you, or might look like it brings out some explanation of things, but it might just be something that's completely
right,
random too, that you're just associating
right,
with something that's special. Now, I'm not saying that that's the
absolutely.
case because I obviously just got here. I haven't really had a chance to see what you
Yes.
presented and whatnot.
So,
But when
fine.
you
Can
say
you?
that you see things come out, go ahead. No, go ahead. I'm sorry.
No, I wanted to ask Fight if he could put up the other picture that I sent him that I got with the
Yeah. Okay.
inversion because yeah. So on your left side, you see it's not in scale, of course. I was just playing around. Actually,
Hmm.
my friend helped me because I am no computer genius. So on your left side, you will see the convex Earth. And with the same formula that I got the Fibonacci spiral, I got the concave Earth, that's the way sun rays work. And this was done with Python. And actually, this mathematician did it on hand because he wrote this book, his last book, in 1990. So he was able to do it in his mind. And but I find it interesting that with the same formula, I get the concave Earth model with light curving and the Fibonacci spiral as well. Oh, this is so
Okay,
hard
you're saying the
speaking in
picture
English,
on
you
the
guys.
right.
Oh my God.
I'll do my best to learn Italian, but I can't promise anything.
Yeah.
Considering that you're doing this in a second
No,
language, I think you're doing
let me.
amazingly.
Yeah, and for me, seeing I'm trying to grasp the concepts that you're trying to convey, and like I said, I'm just now coming into this with no prior hearing of you guys talking yet, so I haven't really heard a true explanation of that. But I would still need to understand. For you to convince me, you would have to explain to me, explain to me how the light does this in the electromagnetic field. What we understand about light is not that light is like physical. It's more of just an excitation in a field. So you would have to explain why we're getting that wrong and show some kind of science. You can mathematically come up with all kinds of pretty pictures, and I commend you for that. At least you're trying. And math is science. You can find, if you can do something predictable with math, then you have a leg to stand on. But if you can just make pictures that don't match reality, that just match what you would like reality to be, then that's not really evidence to support your cause. Because
Right.
then you have to give me something for me to be able to verify for myself, not just a drawing.
Right, right. Well, what was the question? Like, maybe we should do this like again from the start, because we've already been here like for a few hours talking about this, and it would be cool like talking about it. And
Yeah, I think a conversation
but
between you and Team would be pretty good, because Team is much more versed in like general and special relativity than I am. There's areas of physics that I understand better than Team, and there's a lot of areas of physics that he understands better than me. And I think a conversation between the two of you could be quite a good one. So I definitely want to try and get that arranged. But
well, I think that you guys.
Sorry, carry on.
I think you guys know more. I think you guys know much more than me about both of these subjects, general relativity and special relativity. Like I said, I am not a physics. I don't have a physics major, but I do find this transformation from Euclidean space to non-Euclidean space very interesting. So I am sure that you guys will tell me so many things that I'll be like, oh my God, I don't know what the hell you guys are talking about. But at the same time, I think this model is worth a shot, and I will send you the link to a book that has the
I'd
math
definitely
and
like to read that.
that has the information that maybe I will not be able to give you guys because I'm just a girl in Italy.
I want to say thank you for coming on and having a decent conversation with me. I've noticed that conversation with concave earthers are very different to conversations with flat earthers. And I appreciate you having a cordial conversation. I know it's late in Italy there, it's about 2 a.m. So thank you for staying up to do this as well. I really do appreciate it. But we're going to shut down for tonight, guys. The link to Elifaki's channel will be in the description. You might need to learn Italian to watch her videos, but you can certainly go and check her out. Do you have any final thoughts you'd like to say to the people watching?
No, thank you for keeping up, and thank you for inviting me. Thank you to everybody for listening, and thanks for your friend for joining in.
It's been a good conversation. I've enjoyed it. A couple more super chats to go through. Cable Eastwood for $2 says, I want my brain cells back. Draco Fire just left a $1 with no message. Thank you very much. I really do appreciate it. God's Auditor for $2. Tell her to take a college level physics class. I think everyone should take a college level physics class.
I will.
You can take them online for free.
Yeah.
You can literally right now, guys. I'm going to tell you, we all live in a time of information. Okay, anybody can go on, and I'm sorry, I don't want to butcher your name, so I'm just going to say Miss Italia. Okay, Miss Italia. You can actually go on right now, and you can take a college level physics course not to understand the physics, but to understand not to agree with the physics, but to understand the position your opponent comes from. It strengthens your argument when you can be able to use your understandings to fight what the scientific consensus is, and that's the only way you're going to win over somebody like me or fight or anybody that's in the crowd right now. Not with simply saying that this is the way it is and just trust this guy over here, but going and saying this is the way you say it is, and this observation shows that it's not that way. That's the best way to win over, is to show that it's wrong.
Makes sense.
Absolutely.
Jaybird
We talked
Max
about some things.
Yeah. Jaybird Max for
Earlier.
199 says, "You're welcome, bro." That's when I was saying thank you to everyone for super chats, because I couldn't keep doing this channel if you guys didn't support me with super chats and membership. It means the world that you want to support me like that, and I can never say thank you enough. If you're not able to super chat, you can always just share my videos, and that helps just as much. So, and team, this one's for you from GBG Man, and it's just 20 secs.
Yeah, that's awesome. I'll do my sex dance when I have just a tad bit. I'm to be honest with you guys, I'm so drained right now.
Yeah,
like everything that's gone on in the past like 3 weeks has just been like, ugh. But I've got lots of sex dance that I guess, Miss Italia, we have to inform you. Anytime we get Swedish kroners, right?
Yeah.
Is that what sex are? Swedish kroners?
Yeah.
Okay, so anytime we get Swedish kroners, we get on the camera and we dance for them. So,
Oh,
because
really?
Yeah.
I want to see
they're
that.
sex.
It's called the sex
SEKS, sex dance. Because they're
And
SEKS,
before we
but-
go, something I do with Flat Earthers and team does with Flat Earthers is we ask what we call the litmus test questions, right? So the chat has been asking me to ask you the litmus test questions. So if you don't mind, if I have a triangle of sides 1, 1, and 1, what are the internal angles?
Well, it depends if we use a Euclidean geometry or non-Euclidean geometry.
We're using Euclidean geometry. For this example.
Yeah, Euclidean.
Well, then 180.
Yep. So what would each internal angle be?
180 divided by. Well, it depends on the triangle.
An equilateral
If we
triangle.
have like.
Yeah,
Well, then
equilateral.
180 divided by 3.
Perfect. That's better than most Flat Earthers.
I'm going to tell you something. Yeah, and that's so crazy. I think this is the second time we've asked a non-flat earther who we disagree with what the answer to that is, and they come back with the good answers.
Yeah.
Flat earthers are the stupidest people on earth, okay? They're the stupidest people on this, whatever shape it is, on this earth. They are legitimately the dumbest people. There is a reason why
What?
flat earth is filled up with people who cannot agree. Who cares that they can't get the fact that it's 60, 60, 60 on the inside? They can't agree on what the right answer is.
Yeah.
Some of them say, I need a right angle triangle for that. What do I need my triangle calculator?
Yeah.
Give me a break.
We've had people say all sorts, like 69, 45, like 90 degrees for each one. They think it's a square. Okay, next
Oh, really?
question is, what is 5 divided by 0?
0?
Ooh, no.
Wait.
Oh,
You can have a
no.
second chance.
Oh, it would still be 5, right?
No, it's undefined.
No.
Okay.
Undefined.
So my kid, my bigger kid, he's in the 3rd grade, and I have to like watch YouTube videos on how to do basic math. So excuse me, but I don't do math.
That's okay. Team, what's the other one? I've forgotten the third question.
Oh, God. Is 10 to the negative 17th a positive or negative number?
10, wait. I have to 10 to the negative.
Yeah, 10 to the
17.
negative 17.
Yeah, 10.
Is it a negative or a
10
positive
raised to
number?
the negative 17th power.
Oh my God. Okay, hold on. If I'm going to multiply. Well, I have 50-50 chance of getting it right.
Take a guess then.
I'll take a guess. I'll say that it is a, I don't know. Wait, 17? 17 is a dispari, negative. No.
No.
Okay, hold on. No, let me help you out. Before we get off here tonight, I want to help you out in one way, okay? 10 to the negative 2 is the same thing as 1 over 10 to the 2. What's 10 squared? What's 10 times
100.
10?
Yeah.
100.
Okay, what's 1 over 100?
1 over 100 is what is it's wait,
Yeah.
10? No.
1
I'm
divided
not
by
good with
100.
math.
1 divided by 100. Okay, but yeah, 1 divided by 100 would be
I'm not-
0.01. No, yeah, no, that's fine.
Point-
I'm trying to help you out here. Just, I'm not trying to make fun of you or anything. I'm just trying to help you out. Just so you can answer the question in the future if somebody asks you. So 10 to the negative 2 would be the same thing as 1 over 10 squared. 10 squared is 100. So 1 divided by 100 would be like dividing a $1 bill into 100 pennies. So 1 over 100 is 0.01. So 10 to the negative 2 is a positive number. 10 to the negative 17th is even smaller positive number.
But it's still positive.
Okay. Oh,
But it's
yes,
still
I get
positive.
it.
But thank you for playing.
I get it.
I appreciate you taking the time to do that for me. And again, I want to say thank you for coming on tonight. It's been a really decent conversation. And if you don't mind, I'll pass your email along to Team, and you can come onto his channel and have a conversation with him. Oh, I think she's.
Well, I'd like to. At this point, I'd kind of think I want to get her understanding, or like truly understand what she means by Euclidean and non-Euclidean. I mean, I understand the difference between Euclidean and non-Euclidean geometry, but how that applies to the concave Earth.
Yeah.
Because I think somebody tried to use that same thing, that same argument against me, saying that light just naturally curves, like on non-sec, and I didn't have no idea what he was trying to say, because the way he was explaining it as if Earth was a neutron star, and light basically bends around the surface and remains level to the surface, and I was just like, what?
Yeah.
No,
I think
that's not how it
Faki's
works.
connection has dropped out there, but it's cool. Oh, you're back.
Okay.
We can't hear you now. I think you need to turn your microphone back on. Oh,
My microphone?
yeah, no, we can hear you. That's cool. Yeah, you
Okay.
dropped out for a
Yeah,
second there.
but next time I definitely I'll watch this debate later tonight, the rest of it, and that way whenever she comes back on, we can kind of get a better idea of where she's getting these non-Euclidean ideas from.
But a bit of news. I've been just emailing with Ranty Flat Earth, and it looks like me and him are going to be having a debate that will probably be dual streamed on Ranty's Roundtable and on my channel. So that'll be fun. But for tonight, guys, we are going to shut down. I'll just check I've had no more super chats. I've had a couple more. Draco Fire for $2. It's pronounced Draco, Craig. Sorry for getting that wrong. And Raven Zero for $2. Support Team and FTFE. Yes, guys, your support means the absolute world. Coming up tomorrow is another debate with a concave earther, I think. So that should be fun. And then me and Team are working on a video together, but we've also got a couple of videos that will be coming out just before that. So look for that over the next week. Edafaki, thank you very much for coming on and talking with us tonight. It's been an absolute pleasure. And as always, guys, remember, stupidity is not a right. Fight the flat earth. I failed.
Wrong one.
I put the wrong one up. I failed.
Fight the flat. Fight the flat.